Hello everyone. Welcome to another day where we're going to be doing some LeetCode Explore cards. Today we're going to continue in the Arrays 101 LeetCode Explore card, and we're going to do a question that I personally find amazing, and it's going to teach us a lot of new LeetCode related things. So without further ado, let's jump right into it. So you can navigate to this page by going to the Explore tab on the top navigation bar, going to Arrays 101, going to introduction, and finally squares of a sorted array. This is going to be the last one of this introduction section, and then we'll be moving on to inserting items into an array. Again, if you want for me to dive in a little bit deeper into learning how JavaScript arrays work and going over some of these other introductory articles, please let me know in the comments. I'll be more than happy to do a video like that. And if you like what you see, you like doing LeetCode, you like general problem solving, then go ahead and click on the subscribe button and also ring that notification bell so you'll never miss out when I put new content out. So without further ado, let's go ahead and begin. I normally like to open all these questions inside of the actual LeetCode window. I think we retain the dark mode and it also gives us a little more room to work with, which I like. Let's go ahead and read the prompt, and then we'll go over two different ways of solving this question. One of them being probably the naive brute force method that I think a lot of us when we're starting off will think of, and then the next one, which is a little more of an optimized manner of doing it. Cool, so it says, given an integer array nums sorted in non-decreasing order, return an array of the squares of each number sorted in non-decreasing order. So we want to take this array and return the squares of every single number in increasing order. Okay. Now look what it says right here in the follow-up. Squaring each element and sorting the new array is very trivial. Could you find an O of n solution using a different approach? So I think one of the big kickers here is that we're already given this in non-decreasing order. So here, this is a good example to think of, because most of us, if they weren't given this example, and this happened to me, we would almost always be given an input that looks like this: 1, 2, 3, 4, 5, right? Because what you can actually do in this case is you wouldn't even have to worry about sorting it afterwards. You can just go through this array, squaring each one of these numbers and just returning that array, right? But it gives us a little bit of hints that that's not the way of doing it, because it sees that this is in non-decreasing, which this one is also, but we also have negative numbers. When you square this negative number, for example, 16, you end up with something that's larger than, say, 3 squared, right, which is 9. So it kind of just goes to show that you can have a negative number that's squared and end up with a larger value than that of a positive number that's squared. And I know it may sound obvious, but at least when I was starting out, it's a mistake I made, so I want to make sure that we don't make it here. Now let's go ahead and figure out how to do this with this naive way, and then we'll jump into the next piece. So really, we should be able to do all of this in a single line with JavaScript, and I'll show you how to do that right now. The first thing we're going to do is we're going to say return nums.map. So map is an array method in JavaScript that's going to apply a function to every single one of the elements inside of the given array, and then it will return that element and return a new array with that callback function applied to every single value. So in here, what we can do is we can map every single number, and what we want to return is that number squared. So I'll go ahead and use the math.pow method here, and I'll say I just want to return that number to the power of 2. But that's not all, right? We also need to make sure that we sort this. So because map gives us back a new array, we can just go ahead and change our sort method right to this. Sort will take a callback function that will also give us two numbers. We can say num1 and num2. And if we want to return it, or rather if we want to sort it in increasing order, we can do num1 minus num2. Right? If you want to do decreasing order, then we'll do num2 minus num1. It's easy here because we're dealing with just numbers, but if you can actually get very complex here, you can pass in your own function. I mean, we did pass our own function here, but you can make the result of whether or not you want it to be increasing or decreasing a more complex expression than just num1 minus num2. So if we run this, let's see what we get. So 0, 1, 9, 16, 100. Looks like it's fine for that first test case. Let's go ahead and run it for the next one. 499, 49, 121. They look fine for both. So let's go ahead and submit this. Make sure everything's working as expected, which it does. And the funny thing is, hey, we're actually getting some good numbers here, right? 83.92 for time and 84.63 for space. However, there's something we can do a little bit better. Let's think about the time complexity here, right? Our bottleneck really is sort. Sort in JavaScript, depending on the browser you're using, most JavaScript implementations, the engine it's running on, and in the case of me, I'm using Microsoft Edge, which runs on Chromium, so it's going to be using the V8 engine. It'll use some variant of Quicksort, which runs an O of n log n time, and that becomes our bottleneck. Now, there is some space. I believe the internal space used by Quicksort is O of n. So let's go ahead and say that this is going to be an n log n time complex algorithm with a space complexity of O of n for that internal Quicksort. Okay, let's see if we can do a little bit better, right? And I'm going to try and draw a picture here and show you how we can do this. This all comes down to using 2 pointers. It uses actually a couple of different techniques that I find pretty cool. Let's think about 4, -1, 0, 3, and 10. So let's imagine we had another array here, and I'm just going to fill it up with empty slots, where each slot, it's going to be the same size as our array up here. These are the empty slots, which eventually will have a number in each one of them. If we know the output's going to be an array that's in increasing order, so we know that this last one needs to be the biggest one. Similarly, we also know that this first one needs to be the smallest one. Now, I've never actually tried going from the beginning, but let's go ahead and start at the end. Now, this pattern of sort of recognizing that the last thing here will be the largest number, let me see if I can explain it a little bit better. There are a lot of questions that ask you to return a sorted array. Depending on the constraints, if you have a constraint that's small enough that you can create an array with a fixed size, right? Like imagine I asked you to just take like random numbers like 5, 4, 3, 7, and 9. And I told you that each of these different numbers will never be larger than 100. You can create a new array that's of size 100. Imagine this array here of size 100, and then place these in their respective areas, right? So 5, 0, 1, 2, 3, 4, 5 will go here, right? 4 will go here, 3 will go there, and then 7 will go wherever it needs to go, and then so on and so forth. This here will be left with an array in increasing order, but if you want to just return the same array in decreasing order, we can just loop through this array starting from the end and go all the way down and maybe just push these elements into a new array and return that. So it's almost like sorting just by the nature of where the elements are placed in the array, and this normally works well for questions that have small constraints. That's sort of what we're taking advantage of here. So let's go back to this concept of these empty slots. And what we're going to do is we're going to put a pointer on each one of these numbers. Let's say I and J, right? So let's square both of these numbers. If I square 4, I get 16. If I square 10, I get 100, right? So we need to pick the larger of these two, okay? The larger is 100. So we can place the 100 right here. And since we just did an operation with the value 10, we'll go ahead and decrease J to look at the next number. And now we'll do the same thing again. We'll look at -4 and 3. We'll get 16 and 9. What's the bigger one? It's 16. So we'll put 16 here, and then we'll increase the I, okay? Now we do the same thing. We get 1 or we get 9. What's the bigger one? It's 9. Then we keep going. We just operated on 3, so we'll go down. We get 1 and 0. What's the bigger one? It's 1. And finally, we get I and J right next to each other. Kind of make it like this. Hopefully you understand what I mean by that. I and J next to each other. And it's the last one, so really it's just 0. So let's go ahead and see how we can code this out. Right? The first thing we're going to need is that output array. That's going to be the sorted array. So here we can simply just say const sorted. I'll go ahead and use the array constructor here, and I'll create a new array of length of the nums. And that's exactly what we're going to use to enter things in. Now I normally fill these up with zeros, but in this case, since I'm already going to have the result of the expression, the result of me figuring out which is the larger power when I do the power of 2 for both numbers, that's going to be the thing that I entered at this index anyway, which is going to be overriding that 0, so I don't need to worry about that. This is something in JavaScript that's called a sparse array, and we can actually look this up. Say sparse arrays. I know my spelling obviously isn't very good today. Let's see. A sparse array is one in which the elements do not have contiguous indices starting at 0. Normally, the length property of an array specifies the number of elements. If the array is sparse, the value of the length property is greater than the number of elements. So here, if we do a new array of 5, there aren't any elements, but a.length is 5. Here we can create an array with no elements and length is 0. Assignment adds one element but sets the length to 1001. Okay, I think here it's a little bit better. Let's see if we can, is it notes, sparse? Empty slots in sparse array behave inconsistently. Arrays can contain empty slots, which are not the same as slots filled with a value undefined. Empty slots can be created in one of the following ways. See, array constructor, array 5 empty slots. Consecutive commas in an array literal is 1, 2, 2 empty slots, and then 5. In some operations, empty slots behave as if they are filled with undefined, but in others, most notably array iteration methods, empty slots are skipped. So I just want to give a brief introduction there to sparse arrays, and that's exactly what we're creating here, a sparse array. We don't need to fill it up because we're going to be filling it up as we go through this algorithm. So let's do this. Let's say start equals 0. Let end equals nums.length minus 1. Now we can say while start is less than or equal to end, we'll do exactly what we did, right? So we'll say start squared equals math.pow of nums at start to the power of 2. We'll say const end squared is math.pow nums of end squared. Here we'll say if start squared is greater than end squared. What do we want to do? We need an actual index, right? Here we can say let insert index equals sorted. Let's actually do nums.length minus 1. The reason I didn't do sorted.length minus 1 is because since this doesn't have anything in it, not even zeros, I'm not sure what sorted.length minus 1 would do. So I'm going to be using nums in this case. If start.squared is greater than end squared, it means that the one at start is greater. We need to put that one first. So I'll say sorted at insert index minus minus equals start squared. Else sorted at insert index minus minus equals n squared. And we also need to make sure one of these, so if we're choosing start squared, then we'll say start plus plus, and if we're doing n squared, we'll do end minus minus. Right, so let's think about what we're doing here. Just like we did, right? Start is less than or equal to end. We get the square of both start and end. If start is greater than n squared, then at sorted insert index minus minus, this is a postfix operation, which means the first piece of this expression will resolve first. So we'll actually do the assignment of start squared and then we'll decrement insert index. We always need to decrement insert index because that's where we're going to be inserting the new value inside of sorted. So if start squared is greater, then we know that sorted of insert index needs to be the start one, and then we'll increase start to get to the next one. That way we increase it. If sorted else, we know that end is greater, so we'll make the larger one n squared, and then we'll also decrement our end. And then at the end here, we should end up with just sorted. Let's go ahead and run this and see what we get. So 019, 1600, and 499, 49, 121. So test cases pass both. Let's go ahead and run this. Now, if we look at this, you might be thinking, well, hey, we're getting 34.12. That's not as good as our 83 or 84 that we got before. I wouldn't worry so much about the percentage. Focus on understanding your time and space complexities, right? We went from doing an O n log n operation to now just doing a linear time operation, right? We're only going through nums in a single pass, doing the operations during the same pass, right? We're not having to do one pass for one thing and another pass for another thing. This also incurs a similar amount of space complexity, right? Because we're creating a new output array that is the same size as nums. We can't really do it in place because we need to have these numbers sorted out, right? What we might be able to do, let's see, if I do 4 and 10 and I change this to 100 and then I go to 4 and 3, if I change this to 16 and then I increase the 4, now over here I'm going to be left with -1 and 16, right? Because we actually changed this value. So we're going to need to create a new array. So we now got a better time complexity from going this route. I know it's not it might not seem very intuitive now, but I would recommend that you go through this question, really try and understand it. I hope that the little diagram I tried to put up made sense. Let me know in the comments if you want for me to dive a little deeper, if you like this sort of explanation, or if you want me to maybe try something new. I'm more than happy to do that. I am also learning myself here, so I think it's fun for both of us to get involved. So with that being said, thank you all so much for joining into today's LeetCode Explore card section. Again, we finished up the last piece of the introduction section in the Arrays 101 Explore card. We'll be resuming next time with inserting items into an array. Looking very much forward to going through this entire Explore card with you all. Again, if you like what you saw, make sure you subscribe, click that notification bell. It's really going to help me out for future videos. Until next time, happy coding.